Right. Well, thanks for having me. I want to thank Rubius and the conference organizers for flying me to Mother Russia for the first time. It's been awesome. I've gotten to meet some people that I've worked with for like over 5 years for the first time in person, so it's been really great. So today I'm going to talk about computer vision development in sort of the deep learning era. And I'm, as it says, Denver Dash, Director of Machine Learning at Occipital. Occipital is, in case you don't know who they are, we're a 3D perception company. So we build sensors and software to see and understand 3D geometry and structure in the world. So this is one of our flagship sensors, the structure sensor. This is a new version. It just came out a few months ago, Structure Core. It works indoors and outdoors, and so it gives you like this grayscale image of the scene you're looking at, but it also gives you for each pixel a depth value. And it works indoors, outdoors. It has this global shutter, so very fast objects you can capture very crisply. So it's a pretty cool product. And with that, it gives you a lot more information to understand the world around you if you're building a machine learning algorithm or something around it. We have this other very similar kind of thing. This is it's a color LiDAR mobile sensor. So LiDAR, you know, it's very similar. It's a 3D sensor, but this thing has at the top, it has a 250-degree lens. So light bends down from the bottom and shoots down into the sensor. It's a crazy lens. I didn't even know these things existed, actually. And then it maps for each LiDAR point. It gives you a color value. So it's another thing. This gives you much bigger range than the structure sensor, so you can do really cool sort of outdoor reasoning about 3D structure outdoors. Anyway, that's us. We have a few offices throughout the world. We do work a lot with Russian engineers. We probably, I don't know, close to 20 different Russian engineers in different capacities. So I think it would be great if we could get a Russia office someday soon. I don't know if that's going to happen, but anyway. So I'm going to talk about, this isn't a tutorial on deep learning. There's lots of those out there. This is really about managing deep learning teams and what techniques, general sets of tools they should use, how they should iterate to get to sort of an industrial level product, something you can release to the public, how they should balance their priorities in that process, and then finally, how do you know when you've gotten to that endpoint? How do you know it's ready to release? All right, so computer vision engineering prior to 2014, you had sort of this cloud of techniques that you could access. And these are very different techniques from each other, like graphical models, random forests. You might know very well graphical models, but you don't know random forests. You don't know bag of visual words. So it's a very diverse set of things that they weren't designed to work together. So when you built an application that used these tools, you ended up with something that looked like this crazy kind of Rube Goldberg machine of computer vision, things glued together, right? So typical development cycle for this kind of system, you might have some training data, you've grabbed whatever tools you think are relevant for the product that you're building, and you have basically some test data. You test the system on that data, you get some error cases. And you have basically two recourses at this point. You go back to the toolkit that you have, and you somehow glue something else on there to fix those errors. Or if you have a very strong machine learning component, you might add training data and use that to improve the system. So that's kind of how it used to be before 2014 or so. So today, with deep learning, we have something that looks much more like this. The components that you have to draw from, they're designed to work together with each other. They glue together very nicely and easily in the same end-to-end framework. And so when you build a system, it looks more like this. It's like much more coherent, much easier to maintain and train, and they work a lot better in general. But you still have the same development cycle. You still have this test data, error cases, and then you have this question of how to fix the error cases, right? So the two obvious things are adding training data, going back to your toolkit, and adding things onto your robot. In addition, now we have, of course, we still have that 90s toolkit that we could throw in there as well. So we have these, maybe an HMM you want to put on top of it, or a graphical model to kind of smooth everything. And then another significant difference is that we have this very, very active research community just cranking out new models and releasing the code free of charge for everyone to use at any time. So you have this new external research that's constantly becoming available. And so the question is, how do you balance your priorities when developing? You have these four kind of options of what to do. How do you decide what to focus on? So typical, I've worked with a few different teams developing applications in the past 5 years. Typical prioritization of these different effects are pretty uniform. Like people, they don't really know. It's kind of randomly trying different things and seeing what works based on what they know, based on what kind of data they may have or have access to. My prioritization looks much stronger, essentially. And I'm going to go through this list and I'm going to explain why I think this is a good order in which to pursue these different options. Okay, so the lowest priority, of course, is just going back to the 90s toolkit. If you feel tempted to throw an HMM on top of a deep model, you might want to do this because you know HMMs very well, they're understood, and maybe you have a mostly working system, and this might, you're pretty sure this could fix that system temporarily. So I'm saying resist the temptation at all costs to do this. And the reason really is that you're basically taking it out of this robot and you're basically putting that robot in a Rube Goldberg machine again. You're increasing the complexity of the system. You're making it so you can't train it end to end anymore. And whenever you tweak one little thing, you have to go and tweak everything else. So it just becomes a much more complex system. So the one maybe case, the only reason I kept that arrow there at all, you might want to do this is if you have a system, it's almost working, and there's some urgent need to get it released or something like that. And you know that one of these tools might just kind of be a Band-Aid on it to fix it. So that's the only time I would recommend doing this. That if you do this, I always treat this as technical debt. It's just this is something we want to, at all costs, get rid of as soon as possible, if we can. Okay, so priority 3. So this surprises some people, that this is my third priority, to go back to the model and kind of add layers to it, or add connections, or change the architecture in different ways, or change the hyperparameters. So this activity is crucial at the very, very beginning when you just build the model and you're trying to get it to train. And often you'll see that it just doesn't train. The losses just don't go down at all. And so when you're in that mode, the very beginning, you have to tweak hyperparameters, and you have to get to the mode where, okay, the model's training now, it's doing something decent that you want. Once you get to that point, I treat this as sort of something to do when you're bored. When you don't have anything else to do, essentially. This is something that you can, when you're twiddling your thumbs, you're waiting for data to get labeled or waiting for models to train, you can tweak the architecture, tweak these. But you shouldn't, so I've seen a lot of people, they will do this by tweaking the architecture, then they'll look at a few scenes or whatever, few error cases manually, and they'll kind of manually have this loop of tweaking parameters and improving the model, which is a very slow process. So I recommend don't do this at all until you have, in earnest, a quantitative measure that you can use to just crank through an entire test set and get a value that you can use to see the effect over a huge data set of tweaking these different parameters. And so once you have that quantitative measure, so by the way, that quantitative measure is not always the same as your loss function that you're optimizing in the model. Sometimes the actual thing you care about, it just doesn't fit into that framework. It's not differentiable. You can't actually put it into the model as such. So that's why this is sort of a special step that you need to do separately. Make sure you have the right metric, the thing that you really care about. Once you have that, you can massively vary this hyperparameters programmatically. You don't just tweak one thing and then run it. You put it all in a for loop and run 10,000 different combinations and see which one improves that quantitative metric. And then another trick that we use is instead of, you always want to have the best model that you're evaluating, but when you're doing these hyperparameter tweaks, don't take the best model, don't take the biggest, deepest model you have, because that just takes a long time to train. So start with a smaller model. It's much faster to train. You can iterate these parameters much faster, get a good set of hyperparameters, and then you go back and train the big model that you want to ultimately release. Oops. Oh. Okay. This process is very slow. Expect to fail many, many times. And when you do succeed, it's just going to be a little improvement. And that's why it's really important to do this at a sort of a massive level so you can make real progress. Okay, just skip that part. All right. So priority 2, new external research. As I said, it's always coming out online. So this is basically that iterative process I just told you about. There's thousands of people out there doing that every day, maybe hundreds for the problem, the specific problem you're interested in. So you basically can progress 100 times faster by going and looking through that code and testing it. So it's worth it even though it's hard to do, because there's so many things out there. It's hard to keep track of it all. But it's definitely worth it to always have a consistent effort of pulling in new code and trying it. So the way that I separate the wheat from the chaff, there's basically 2 mechanisms. One is literally following leaders for the problem that you're interested in on Twitter and finding when a new model comes out, right? Then we schedule, in my team, we schedule sort of weekly or semi-weekly code reviews for new models that have come out, and we just test them on our data and our problem and compare them to our quantitative metrics to see how they compare. The other effective way, aside from sort of Twitter, is when the big conferences come out, there's always sort of a big dump of open source code from those papers and those conferences. So those conferences, you can take advantage of the peer review system to understand which are the best out of the thousands of things that have been released in the past month, which are the best, most promising works to try. So what I found is that rarely when you pull something down, even if it works well, it's usually not a game changer. It doesn't just totally solve your problem. But with some tweaking, with some fine tuning on your data, you can actually get something that improves much faster than you could just by tweaking your parameters. Okay, so this brings us to priority 1, which is the data. So this is by far the most important way to improve your model. And I have a good example in a bit I'll share with you about this. I recommend that the first thing you do before you get too serious about the model is to invest in this data infrastructure. Make sure you have your data in a database, not in text files, for example. Make sure you have the ability to measure error on the whole database and quickly label data and collect data and the whole data pipeline from end to end. The more you can invest in that, the better off you will be sort of in the medium term. Another important thing is think carefully how to augment your data. And this is something that, it's sort of a bread and butter thing in deep learning these days, augmenting data. But if you can, so the problem is that you're trying to solve a problem, and that problem, you're trying to find all the sources of variation in that problem, right? So take hand tracking, for example. You have basically 3 sources. Say you want to track hands in an image. You have 3 sources of variation in that problem. You have the different poses that the hand can take. You have interpersonal variation in those poses. People can hold their hands differently, so people add sort of a level of variation. And then finally, you have sort of the hardest thing to deal with is the background. You have all the different types of background that hand might be on top of. Right? So you can factor that problem into these 3 different components And if you can find a way to avoid having to collect all three of them at the same time, like first collect just empty background with no hands and compose a hand on top of that background, you're augmenting your data like by orders of magnitude, just by coming up with some clever way of generating all this different variance that you'll encounter. Okay, this is getting boring. All right, so let's skip on. So a case study on data. So prior to Occipital, I was director of this hand pose tracking at Magic Leap. So I'm going to tell you a little anecdote from my time there that kind of makes the point, all this point that I'm trying to make, essentially. So I don't know if anyone's tried Magic Leap or even knows what it is at this point, but it's an augmented reality device. You put it on, and you can see virtual content in the space you're in, right? And so the hand tracking effort, they have a controller that you can use, so you don't necessarily need to track hands to use the system. But we do have the ability to do that. And this is one of the sort of flagship released products that or experiences that use hand tracking. It's called Tonande. It's a collaboration with Sigur Rós. And you're walking in your room through sort of this really trippy light forest with crazy creatures flying through the air, like jellyfish floating through the air. And you can touch everything. And the cool thing is that people tell us when they do this, almost always the first thing we hear is that when you actually reach out and touch one of these things and it responds to your touch, they feel a haptic sensation. Like that you hallucinate the sense of touch. So to get that level of precision and robustness, for all people in all environments, it's a intensive engineering effort that has to happen. So Magic Leap is a super secretive company. They wouldn't want me to share any secrets. But when I left the company, I found this notebook which had these notes in it, and I figured, we're in Siberia. They're not gonna find me here. They're not gonna know anything about this. So just as long as we don't videotape it and put it on the internet or something, it'll be cool. Right? Okay. So anyway, this is a handwritten note from my time at Magic Leap. On the left, the X's. This is sort of a standard computer vision model that the pre-2014 kind of model, basically based on random forests. It still had a heavy machine learning component to it, so we used data a lot. And we started with that. We were in early 2015. Deep learning was making a point, but it wasn't. I don't know. We didn't have, for this particular problem, there was no deep learning solution at that stage. So we started with this random forest model. And we spent a lot of time doing that original development cycle for the pre-2014, going back and adding handcrafted features to the system and improving it steadily over time, adding data, improving it. And we had this target number at the top that we were trying to hit, right? So at some point we decided, okay, well, deep learning is making a splash. We need to start looking at that as an alternative. So at some point, I don't know, maybe around March, we started looking at deep learning models. And they could just not compete with the random forest models at first. Okay, so based on that, most of our engineering effort was spent on random forests. And basically 1 year later, four man-years later of adding new features to that random forest model, we basically had achieved our target level. And we got to the point where we felt like we might be almost ready to release this thing. We need to do sort of a massive test on a huge set of data to see if we're going to get to that super precise, super robustness that we need to have to release a product. So we went through this sort of 6 months of intensive data collection and sort of clever data augmentation, as I mentioned earlier, to kind of factor in all the different sources of variation for this problem. And so we still had this deep model coming along. It was kind of trailing the random forest. We had not put we put almost no effort into that model at all because it just wasn't, we couldn't find a way to get it. At this point, we had kind of given up on it for the most part because we needed to release a product. We had the random forest, it was working. So it was just kind of coasting along there. When we brought in new data, we'd retrain that model and it'd go up a little bit. So we thought, well, with this big injection of data we were going to get, maybe that deep learning model, even though we hadn't been putting any effort into it, maybe it would start to approach the level of that random forest model. And so we were kind of looking forward to this experiment that we were running. And what we found was actually really stunning. Because despite all that human intelligence that we had put into the random forest model, the deep learning model just shot above our target value and got to almost nearly perfect accuracy, just based on adding this data. So just to be clear, this model that was nearly perfect here was almost the exact same structure of the model that we tried originally. I mean, at that point, we were iterating a lot on the structure, but we kind of got the best one, and that was it. And we didn't change the structure at all. We just had a huge set of data, and it totally dominated 4 years of development of tweaking parameters and stuff like that. So that's where I'm coming from. This is why I have my prioritization. It's a big part of it. But also, if you just look at the set of deep learning sort of super problems, the problems that have achieved superhuman accuracy, it is essentially a laundry list for the problems that had the best data, right? So ImageNet was the first kind of original problem that deep learning solved better than humans. And it's obviously, it's significant because it was the biggest data set of its kind at the time. DeepFace was built on Facebook's face recognition, face data. So it had basically the whole world's labeling data for it, a huge, very unique set of data. OpenPose was built, there was a CMU, they had this studio where they could basically generate infinite data, infinite label data by just putting people in this big panoptic studio, and they'd use multi-view geometry to track the joints and they'd label the data. So all of these AlphaGo and DeepQ learning, these were programs that played themselves and so could generate infinite data. So all these were pretty impressive, and it's all because of the data that they achieved that superhuman accuracy. So one special interesting thing is AlphaGo 0. AlphaGo 0 differs from AlphaGo. I assume you all know what AlphaGo and AlphaGo 0 are. It differs from AlphaGo in that they totally removed all human knowledge from the system. And they just said, you just play yourself, and without any, we think we know better what it should focus on. So AlphaGo had a lot of human knowledge. This was just you play yourself and you decide the best way to do it. And within less than 5 days of training like that, it could beat AlphaGo like 100 out of 100 times, essentially. And then, 40 days later, it could beat sort of a coalition of 60 Go masters online or something like that, like 100% of the time. So it's not just the amount of data, it's also the quality of data, the kind, non-biased data that's important. All right, so how am I doing on time? Okay, all right. Okay. So the last thing I want to talk about is how do you know when you're done with a system like this? And this actually raises some philosophical questions that differ from sort of the academic pursuit of machine learning versus industrial pursuit. Imagine you sort of followed my advice. You have this super refined data machine where you can collect data, label it, incorporate it into your model at will. Okay, you have this kind of engine you can just draw on to get whatever data you need. So the problem is, as you iterate in your development, normally you would have a test set separate from a validation set, separate from a train set, right? And you would, you iterate on the validation set, and then when you're ready, you test on the test set, right? Now we're developing a product here, and this might take a year to release, so we're going to hit that test set multiple times, right? So how do you know? So let's say you just have this graph on the left of improvement. You're improving, and then you get to your target value. How do you know that you're not just overfitting to your test set at that point? You've already hit the test set 10 times. You've tried not to, but it's inevitable. If you want to check your progress, you have to hit it occasionally. So the way I approach this is, I start with a train set, a validation set, and a test set. Let's just say train and validation are lumped together. So you do your iteration. You maybe you find a new external model that increases a big jump in your accuracy. You iterate, you clean data, you do hard negative mining, and you get over that value. And then you want to know, is this real or is it not? So what you do is you purge your test set. The test set gets folded into the train set, and you collect a whole new test set, twice the size, if you can, of the original test set. So when you do that, because you've increased the size of the test set, you've hopefully found some sources of variation that weren't present before. It's a much bigger, harder test set. So you expect to see this drop of accuracy. And then you just continue the process. You keep iterating, tweaking, and you cross that threshold again, and then you do the exact same thing. You fold that test set into the train set, and you collect an even bigger test set. And again, you'll start to see a drop. And the hope is that as you progress, this drop gets less and less each time, right? You iterate, you cross the threshold, double the test set, and eventually you get to a point where you don't drop below your target with that new giant test set. And that's when you feel confident you're not overfitting to your test set. That's how you know you're done. All right, and that's pretty much it. So summary, avoid non-deep methods. Invest in a data machine so you can crank through and just have this engine testing and training very fast, automatically, vary your hyperparameters in a giant for loop instead of manually. Stay up to date on recent research. Tweak your hyperparameters when you're twiddling your thumbs. And then detect when you're done by incrementally purging your test set. That's it.
Hi, thank you. So my question will be related with Twitter. Can you please give us an example when Twitter really helped you? Maybe some interesting example you have.
Well, I can give a general example. I don't want to be too specific because it's actually still something we're actively working on. But just very recently, actually, we just discovered a new. So we've been working at Occipital on understanding 3D with just color sensors, not with our fancy depth sensor, but if you just had a regular sensor, what can you get out of 3D? And we've been working on it for almost a year at this point, and pretty much going through this process that I described. And just in the past couple months, a model came out that I found out about on Twitter, and it way outperformed anything we were doing. Yeah. So so now we're using that one and we're iterating on that one. And, yeah.
Okay, got it. Thank you.
Yeah.
Ребят, руки поднимайте, кто готов спрашивать. Maybe I have a... okay, Кирилл, давай лучше ты.
So I had a question on this last step where you said that you double the test data set. So you double it from the training data that you were using before, right?
Test data.
Test data.
Yeah, and then the old test set gets folded into the training set, so it increases as well, but not as much.
Yeah. So basically you do that by adding more training and test data and increasing your general data set?
Say again?
So basically you're doing that by increasing your general data set, by just adding new data there?
I'm increasing my general
data set?
Yes, you need to get new instances in order to do that, yeah.
Okay.
Is that the
thanks.
question?
Yeah. Well, the question was actually, yeah. So you were populating and adding more test data, and you're taking it from the data that you used for training before.
No,
it's
you're
brand new
collecting
data.
new data. So that's part of
Okay.
the data machine that you have, the investing in data tools and labeling and data collection. So you have to have that. It has to be easy, or else
Yeah.
this becomes a pain in the butt, right?
Yeah.
So yeah, and so this doubling is sort of an ideal situation. It may be too costly for you to do that,
Yeah.
but just hopefully you increase the size at least. Yeah.
Yeah. Thanks.
Вот еще вопрос.
I have a question about how you validate that your data machine produce correct data, that there is no some hidden caches, hidden relations between data, that it covers full spectrum of data and so on.
Yeah, you do that by testing the system live, not on data, but on real instances. It's basically like collecting more data, but you don't have to go through the whole labeling process. You just put the system in the context that you're going to run it in real life, and you'll start to see it sucks. And so then you know something's wrong, and then you try to ask yourself, what about that situation is different from what I have?
So, but how you detect what's wrong? Your model or your data?
I mean, by the time, in my experience, it's a good question actually. I don't have an answer exactly. I mean, it depends on the situation, but in my experience, once you get into this mode where you're chasing that target and you're making progress and you're seeing continual progress, your model's pretty good. Maybe you get to the point where it flattens out, and then you say, okay, I'm not making progress anymore. The model maybe needs to be deeper to account for more variation in my data, right? Then you start to maybe add to your data. But if you keep seeing it go up, you hit the target, and then you test it and it sucks, that's probably a lack of variation in the data. At least that's one problem. It might be both. Yeah, right. So, but then almost you know that the data is not correct because it didn't detect that suckiness. Right?
Thank you.
Ребята, руки. Finally, I have a chance to ask you. You'll be after me, okay? You mentioned a little bit about Magic Leap. So my question is, what should we expect in CV technologies in the nearest future? When would it be? Maybe online recognition of free gestures or something like that, something rule-breaking technology?
You mean for Magic Leap or just in general?
Maybe in general. Maybe I'm convinced you know more about it.
Well, I think the biggest frontier right now in computer vision, and maybe I'm biased because I work at Occipital, it's partly why I work there, is the understanding 3D. Up till now, most of the things I showed you there were 2D problems, the things that are beyond human level accuracy. Even the human pose is just 2D pose. It's not where is that person, how far away from the camera is that person. So that stuff is now just for the past year, I'd say, becoming big, and it's due to new data sets coming out that just like ImageNet data, it's 3D and it's big, and we can start to build models and reason about 3D. So I think that's where we're really going to see gains, and that's really important for things like robotics, and that's a real scene understanding. Like when we look at an image, we have an implicit understanding of the 3D structure usually. So until we get that, we don't have real understanding. Right?
Thank you. So who's next?
First of all, thank you for your talk. I wanted to ask, you mentioned that your data has to be not biased. how do you make sure it's not biased? How hard is the process? Is it what scale it is?
Yeah, it's kind of like what he was asking. If the data is telling you your model is good, and then you run it in real life and it's not good, then you know there's something wrong with your data. Either it doesn't have that variation in the real life, or it might have it. It might look like it have it, but maybe you've done something to it to bias it. Like, for example, if you do some kind of compositing of, like I said before, compositing the foreground with the background, that could introduce artifacts that the model can detect that composition. So if you do stuff like that, you should always have a certain fraction of non-composited data as well, so that the model will catch that artifact that you're introducing.
Okay, so it's basically a trial and error.
Yeah,
Oh,
absolutely.
okay.
This whole thing is trial and error. It's basically massive trial and error. Yeah.